Okay, so now we are going to talk about an important algorithm called Prim's algorithm. This algorithm has a very important structure which is going to keep coming up once again. When we look at shortest path problems, what we will find is the same structure is going to come up. It's a greedy algorithm for building a minimum spanning tree, a minimal spanning tree of a given undirected graph, weighted undirected graph. It's a greedy algorithm for building a minimal spanning tree. How does it work? Here is how it works. So the first thing that Prim's algorithm does is it's going to grow a spanning tree. Starting from a single node, it's going to start growing a spanning tree. So the intermediate state of Prim's algorithm, the intermediate state is going to be like this. It's going to grow a partial tree. So it's going to grow a partial tree involving some of the nodes in this graph. It's going to grow a partial tree, let's say involving 1, 2, 4, and 5, but then some of the nodes are going to be outside this tree. So let's call this partial tree involving S. S is the subset of nodes that I have built a tree for. Okay, and then V minus S is the remaining nodes in the graph for which I have not yet built a tree. Okay, now it's going to be greedy in the following way. At every step, it's going to consider the edges that cross the boundary. What does that mean? So an edge that goes from some node in the tree to some node outside the tree. So it's going to look at these edges that go from some node inside the tree to some node outside the tree. Let's say edge weight is 4, 2, and 1. Okay? So it's going to look at these edges that cross the boundary, and it's going to take the minimum weight edge that crosses the boundary right, which is going to be in this case 5 to 7. It's going to take this edge and add it to the tree. So it's going to add 5 to 7 to the tree, which means it can no longer add 4 to 7, and then the tree becomes, so the tree becomes, so 7 gets added to the tree. Now 7 is part of the family, so the tree, so let's call this edge E. So the new tree is the old tree union E. So add this edge to the tree and keep going and keep going. And what you will end up doing is find the MST at the end of it all. Okay? So let me take an example and illustrate exactly how this happens, and then we'll come up to the bookkeeping part of this algorithm, right? So there's two parts of this algorithm. One part of this algorithm is at a high level. Why does it work? How does it work? And then how do we make it work in a computer? What kind of data structures do we use to do all the bookkeeping? All right. So I will take an example now and show you exactly how Prim's algorithm works on this example. All right. So let's take an example. Let's take a 7-node graph. All right, and let's add some edges to this graph. All right, so these are going to be the edges that I'm adding to this graph with edge weights shown already. All right, so how does this algorithm work? So first, starting off, the tree is the empty tree. So I'm going to write down the tree, the edges in the tree. So starting off, the tree is the empty tree. All right, let me seed this tree by adding some node to it. So let me add the node, I don't know, what looks like a good node to start from. Let's start from the node 4. So to begin with, 4 is the only part of the tree. And what are all the edges that cross the boundary from the tree to the non-tree part? So 4 to 2 is going to be edge weight 1, 4 to 3 is going to be edge weight 2, 4 to 6 is going to be edge weight 3, and 4 to 7 is going to be edge weight 1. Did I miss anything? 4 to 2, 4 to 3, 4 to 5, sorry, I think I confused myself. Let me draw it again. 4 to 2, 4 to 3, 4 to 5. That's it. That's it. Those are all the boundary crossing edges. Everything else I'm not going to bother drawing. So these are the edges that go from the tree to everything that's not the tree. So currently the tree only involves 4. Okay, no edges in the tree. Just one node 4, no edges in the tree. What's the minimum weight? So this has weight 1, this has weight 2, this has weight 1. So the minimum weight boundary crossing edge can either be 4 to 2 or it can be 4 to 5. I can add either one. Let me choose to add 4 to 5. So therefore the tree now has the edge 4 to 5. This is an undirected edge. It also means 5 to 4. So the new tree after the first step is going to have 4 to 5. This is going to be the new tree. Now what are the boundary crossing edges? Well, I'm going to have the same edges, so then edge of weight 1 to 2 and edge of weight 2 to 3. From 5 I'm going to have an edge of weight 1 to 6, and that's it. The edge of weight 1 to 4 is internal to the tree. I'm not going to add it. So these are the boundary crossing edges. Now what's the minimal boundary crossing edge? Well, 4 to 2, or I could choose 5 to 6. Let's say I choose 4 to 2. So I add 4 to 2 to the tree. So now the tree becomes (4 to 2, 4 to 5). Okay. So then what are the boundary crossing edges? Well, I have to add 2 is the new node that's gotten added to the tree. I just need to consider what are the new things that 2 brings in. So what does 2 bring in? 2 has an edge to 3, but 3 is already okay of weight 1. 2 has an edge to 1 of weight 1, and 2 has an edge to 4, but that's already internal to the tree. So this is going to be the boundary crossing edges. They are going to be 4 to 3, 5 to 6 as before, 2 to 3, 2 to 1. All right. Now let us say we give in and add 5 to 6. Okay, so that's the minimum weight boundary crossing edge. So we add the minimum weight boundary crossing edge at every step. So now the new tree has 4 to 5, 4 to 2, and 5 to 6. So it's 2, 4, 5, and 6 with these edges, okay, shown by the box. So that's going to be the tree. Now what are the boundary crossing edges? Well, since I added 6, what more does 6 bring in? 6 has an edge to 3 of size 3, so it's size 3, weight 3 here. 6 has an edge to 1 for 5, that's not going to be boundary crossing. All right, so what is the minimum weight boundary crossing edge again? Well, I can either add 2 to 3 of weight 1 or 2 to 1 of weight 1. Those are the two candidates. Let me add 2 to 3. So when I add 2 to 3, the new tree becomes, okay, so the new tree becomes 2, 3 is added to the tree. So the new tree becomes this, 4 to 2, 2 to 3, 4 to 5, 5 to 6. And what are the new boundary crossing edges? Well, the new boundary crossing edges are going to be whatever 3 brings in. So 3 is going to bring in an edge to 6, but that's internal to the tree, so I'm not adding it. An edge to 7 of weight 1, okay. An edge to 2, but that's internal to the tree. Edge to 6, edge to 4, 4 is internal too. So this is going to be the new tree. And so I'm still showing you the boundary crossing edges. There are 2 of them from 2 to 1 and 3 to 7. I can add either one because they are the same weight. So let me add the edge from 2 to 1 So when I add that edge from 2 to 1, there's a new boundary crossing edge from 1 to 7 of size 2. Now the minimal boundary crossing edge is again 3 to 7. So once I add that, my minimum spanning tree is complete. So it's going to be all nodes are added to the minimum spanning tree, and it is going to be this. So what's the basic algorithm? So the basic algorithm is while size of the tree is less than the number of so the size of the tree is less than or the number of nodes minus 1. So the tree has less than. So initially the tree is empty. Take the set S to be any node j, where j is any vertex. Okay. Now the idea is while the tree is not full, while it still doesn't include, or you can say the number of edges in the tree. So these are the edges in the tree. These are the nodes in the tree. So while the size of S is less than n, n is the number of vertices. So while S still doesn't have all the vertices in the graph, take minimum boundary crossing edge okay, take the smallest boundary crossing edge and add it to the tree. All right, and which means that when a new edge gets added to the tree, the destination node of the edge gets brought into the tree. The size of the set S increases by 1. The tree gets one more node. You keep adding it, and you're done. All right, so the minimum weight boundary crossing edge is going to be how this algorithm is greedy. All right, so there's two things I have to convince you. First thing I have to convince you is that at the end of this algorithm, the tree that I obtain is going to be a minimum spanning tree or a minimal spanning tree. Can I convince you of that fact? Why is Prim's algorithm, following this minimum boundary crossing edge principle, going to always find a minimum spanning tree? Okay, let us talk about the reason why. All right, so let us say that it is not the minimum spanning tree. So what am I going to show? So first of all, let me back off. How do I show it's the minimum spanning tree? Well, if I take the tree that's been found by Prim's algorithm, let's say I take some tree that's been found by Prim's algorithm, and let me add an edge E that's not in the tree, that's in the original graph but not in the tree. Then if I traverse the path along this edge, if I traverse all the edges along this, then the weight of E and the weight of F, let's say take any tree edge along this path, then weight of F must be less than or equal to the weight of E. So if I traverse this path from the source of the edge to the destination of the edge, it's an undirected edge, so anything can be the source, but if I traverse this path along the tree from the source to the destination of this edge that's not in the tree, then every node F, every edge F along this path has to have a weight that's less than or equal to the weight of this edge. If I can prove that, then I know it's minimum spanning tree. And this is what I called in the very previous lecture the main principle. All I have to convince you is that this principle works. Okay? So how do we know that this principle works? Well, let us examine what happens in Prim's algorithm. Well, what happens in Prim's algorithm is that at some point, one of these, so let us call one of these nodes V, U, and another node V. So let us call this edge UV. The new edge that I am considering E, let us call it UV. I used to show it in green, let me show it in green. So E is UV. Well, at some point in the running of the algorithm, you had to have the following situation. U was in the tree that was growing, and V was outside the tree that's growing. All right, or the other way around. V was in the tree that's growing, and U was outside the tree that was growing. All right, so this had to happen at some point. Okay, one of these had to go into the tree first, and then the other one had to go second. Okay, let us take that as the given. All right, if we took that as the given, and without loss of generality, let's call u the thing that went into the tree first, and then v the thing that went into the tree second. So let's call the node that was in the tree first while I was doing Prim's algorithm u, and the node that was outside the tree at that point, let's call it v. So here is our edge e that was going from u to v. All right. Now, because I did not add this edge, because I did not choose this edge did not end up in the tree, then every edge that ended up in the tree was boundary crossing. So this is going to remain boundary crossing until v is also inside the tree. So until v comes inside the tree, this edge is going to remain boundary crossing. But every edge f that was being considered had the property that wf was less than equal to we, because f was also boundary crossing. But what was the nice thing about f? It was the minimal boundary crossing edge. So either its weight was strictly smaller than that of e, which is why it was chosen over e, or its weight was equal and it was chosen over e purely as a tie breaking mechanism. But any edge that was connected to u must have had a smaller weight than e. So the whole thing, so what are the events? So until v got into the tree, so until v got added into the tree, this edge was boundary crossing. The edge from u to v, which was not in the tree, is boundary crossing, which means that every other edge that got added until then had a weight which was less than or equal to that of e, which means that all of these edges which had to be in the tree until which had to be boundary crossing at some point or another until v got added, must have been of weight less than or equal to that of the weight of e. So therefore, Prim's algorithm by its very construction guarantees that if I traverse this path from u to v, well, every edge along this path had to be boundary crossing at some point and was chosen in preferentially over the edge e. So its weight had to be less than or equal to that of e. And therefore what? Therefore, the path here, every edge along the path has to have weight less than e. So therefore, the final output of Prim's algorithm has to satisfy that principle of being a minimal spanning tree. And therefore, Prim's algorithm always produces a minimal spanning tree. I hope this is clear. I hope it's clear why this effect of taking the boundary crossing edge at all steps will in fact end up getting you a minimal spanning tree, because it ends up satisfying, quote unquote, the principle from the previous video. I hope you remember the principle, and I hope you can see why is it that any edge that's not considered, that's not in the tree, has to be of weight larger than every edge in the path from the source to the destination. All right, if that's clear, then the next step is to show how the bookkeeping is done for Prim's algorithm, so that we can always find this minimum boundary crossing edge with no fuss. So finding this minimum boundary crossing edge might require a lot of work at every step. How do we do it efficiently? How do we data structure this? How do we do the bookkeeping? We'll see that in the very next video coming right up. Okay, so now we're going to look at the bookkeeping part of Prim's algorithm. So far we've studied Prim's algorithm in a very abstract form. Now we have to look at the bookkeeping part of Prim's algorithm. All right, so reminding you of what Prim's algorithm was, you had a partial tree at some point, and you found out of all the edges that are crossing the boundary for things in the tree and things not in the tree. You found out the minimum weight, it should be minimal weight boundary crossing edge. So one way of doing this minimal weight boundary crossing edge is at each step iterate through all the edges in the graph. If the edge goes from a node that's not in the that's in the tree to a node that's not in the tree, it's boundary crossing. Well, among all the boundary crossing, accumulate and find the minimum weight boundary crossing, add it to the tree, rinse and repeat. Well, the problem with that is it's going to take a long amount of time and it's going to be expensive to do that. So we need to do a better job of bookkeeping. And here is how we are going to do the bookkeeping. Rather than look at from the tree out, let us look at from the outside in. So what we are going to do is we are going to do the following. So at every step, for every node that's not in the tree, for every node not in the tree, do what? So for every node that's not in the tree, we are going to maintain two things. Number one, we are going to maintain node dot min w. Okay, I'm going to call it min w. Let me just call it w or d. Let me just call it d. So node dot d is going to be the weight of the minimum weight edge from that node to some node in the tree. So for example, let's take this node 1 and let's take this node 7. So suppose 7 has a edge of weight 1 to 1 and as an edge of weight, let's call this node 3. Let's say it has an edge of weight 2. Let's say it has an edge of weight 0.5. Okay, so take all the edges that go from the node that you are interested in to some node in the tree. Okay, so n dot d is the weight of minimal weight all edges from n to some node in the tree already in tree. So it's the minimal weight of all edges from n to some node already in the tree. So for 7 dot d is going to be 0.5 because that's the minimum weight is going to be this edge, which is 0.5. So I'm not going to worry about bookkeeping this two edges of 1 and 2. Got it? All right, so that's number 1. So I'm going to maintain n dot d, and to n dot pi, which is going to be this minimum weight edge, the destination node for this minimum weight edge. So 7 dot pi, let's call this node 4. So in this case 7 dot pi is 4, 7 dot d will be 0.5. So that's telling me that from 7, the minimum weight edge to the tree, these are undirected edges, so don't worry which is from and which is to. But from 7, just to say it out loud, from 7 the minimum weight edge goes to 4, and that's denoted by pi, and the d, the weight of this edge, is 0.5. So this is going to be what is the information that's stored in every node not in the tree. That's not in the tree so far. So that's so far not in the tree. Once it's in the tree, I don't care. Once it's in the tree, I don't maintain anything. That's number 1. Now you may ask, what happens if a node is not yet connected to the tree? So maybe a node is connected to another node which is connected to the tree. So let us take a node n like this, which is not directly connected to the tree. Well, then n dot pi, let us store it as nil, not yet connected to the tree. N dot d, let us be plus infinity, some big weight, to say that it's not connected to the tree yet. So not connected, not yet connected to the tree. Okay, so far? So it's not yet connected to the tree. So I'm going to store 2 bits of information for every node that's not in the tree. N dot d, which is the minimum weight of all edges from some node to a node already in the tree, and n dot pi, which is the destination node for this minimum weight edge. All right, now here is the idea. So suppose a new node, for example, here is, let's call this node 8. So suppose 8 was absorbed into the tree. So suppose the tree absorbed 8. So 8 went from being outside the tree to being inside the tree. How do I update this information? How do I update this information for everyone else? So first of all, the information will only change for nodes that are connected to 8. So the ones that are connected to 8 are the only nodes whose information could potentially change. Other nodes will not change their information. Okay? Anything that's already connected to the tree but not to 8 is not going to change its information. The only nodes that are potentially going to change their information are the ones for which there is an edge from 8 to outside. And suppose we do that, how do we update? So for example, here is 7 and its current minimum is from 7 to 4, which is 0.5. And suppose 8 comes in and the edge from 7 to 8 has a weight, let's say 1. Well, 7's information doesn't need to be updated because the minimum weight is still the edge from 7 to 4. For 7, it's still 0.5. Okay? Now what if there was an edge from 8 to 9? Let's say 8 to 9, 9 is right here. And then let's say the original smallest weight for 9 was 10 and 9 to 5, let's say. But the new edge coming in from 8 had a weight of 1. Well, then 9.d is updated to 1 and 9.pi is updated to 8. And the new edge from 9 that's relevant is going to be the edge from 9 to 8. So this is how the update is done. So two things need to be done. Bookkeeping. Number one, bookkeeping. For every node n not in the tree, I'm going to maintain an integer or a number called d, which is the minimum weight of all edges from n to some node already in the tree. I'm going to update something called n.pi, which is the destination for this minimum weight edge. So I'm going to keep what is the smallest weight edge, the weight of that edge, and the edge itself through d and pi. Okay? And how do I find the minimum boundary crossing edge? Well, the minimum boundary crossing edge is for every n. So it's going to be the minimum of n.d for all n that's currently not in the tree. So the set of nodes in the tree, let's call it S. So for all n that's not in S, find the smallest one with the smallest n.d, and that is going to give me the minimum weight boundary crossing edge. So this has the following idea. So the idea is I'm going to maintain a min heap of all the nodes not in the tree T. And the key for this min heap is going to be the node.d is going to be the key for this min heap. So I'm going to keep a min heap according to node.d. Okay? So if I do that, at every step, if I extract the minimum from this min heap, then that is going to give me the boundary crossing edge. So if I extract the minimum element from this min heap, which is really, really simple. I can extract the minimum element from min heap and update the heap in log the size of the heap time. All right. So if I did that, then I get the minimum weight boundary crossing edge. So what are the steps of this algorithm? So what are the steps of this algorithm? Very simple. The algorithm has the following steps. So I'm going to maintain a min heap. So I'm going to initialize every node. So I'm going to initialize for all nodes in the graph, initialize n.d to infinity because the tree is empty. There is no edge in the tree, n.pi to nil. So this is my initialization. And then in heapify all the vertices according to, and that's trivial because all the vertices have key plus infinity. You can heapify in any order, it's fine. You can just maintain an array, that's fine. All right. Now what? So this, let's call the heap h. So while h is not empty, n becomes extract min So extract the smallest valued node from the heap. That's going to also correspond to the minimum boundary crossing edge, exactly how we have shown. All right. So therefore, in the very first step, when you extract the very first node, n dot pi is going to be nil. But if n dot pi is not nil, the edge is going to be from n dot pi to n. Okay, add e to the tree. Add e to the tree. Number 2, for all edges from n to m in the graph. So go from n, the edge that you just added to the tree, to all outgoing edges m. If m is not in the tree, so if m has not yet been inserted into the tree, what do? You say m dot d equals minimum of m dot d, comma, the weight of this edge from n to m. Okay, and based on that, update m dot pi as well. What are we doing? Well, we are looking at all the new edges that could be boundary crossing, all the new edges that could be potentially boundary crossing, and we are looking at their target. So if m is already connected to the tree through some edge of weight w, and this weight w hat is less than w, then I update the smallest edge from m to the tree to w hat and update the destination. Otherwise, I keep the old value w. That's all I'm doing for all the edges outgoing to n. All right, and this is the entire algorithm. This is Prim's algorithm. This is exactly the old algorithm, which is find the minimum boundary crossing edge and add it to the tree, except that it's been done now with some bookkeeping. And the important thing to understand about the bookkeeping is what is maintained for every node. What is the meaning of n dot d and what's the meaning of n dot pi? If you understood that, if you understood the bookkeeping, then all of this is easy, and all of this is achieved through a min heap. Now, what is the number of times this algorithm runs? So how long does this loop run? So the size of the heap is going to be the number of vertices. So the size of the heap is originally going to be the number of vertices, because all the vertices are going to be in the heap. And every time I run this algorithm, the size of the heap is decreased by 1 because I extract one vertex out of the heap. So this loop runs as many times as the number of vertices in the graph. The outer while loop runs as many times as the number of vertices in the graph. What's the time to extract the minimum element of a heap? Well, the time to get the minimum element is order 1 because it's always the first element of the heap. But I need to delete it as well. So the time to delete it is log the size of the heap, which is in the worst case log v. All right. Now, what about updating all the edges? Well, so this is going to be for every edge, I'm going to iterate through the adjacency list. So this overall is going to happen once for every edge in the graph, only once for every edge in the graph. Now, what's the complexity of this? Well, this is going to reduce the key. And so it may trigger a bubble up operation in the heap. Because it may trigger a bubble up operation, this will take another log v time. So the total amount of time taken is going to be v log v plus e, the size of the edge of the graph, because you are going to touch every edge in the graph once as the loop runs. So cumulatively, you are going to touch every edge in the graph once, and that's contributing this e here, and this v log v comes from, and you are going to run this outer loop v times, and each time you run the loop, there's going to be a log v time heap operation here, and there's going to be a log v time heap operation here. Because of these two, you're going to get theta v log v plus e. That's really, really fast even for very, very large graphs. Okay? So this is very, very important. The reason why we study this algorithm is not that it's the best algorithm for finding minimum spanning trees. Arguably, there is a slightly better algorithm depending on how big and how sparse the graph is. Let's leave that aside. It's a very, very good algorithm. It's also a greedy algorithm, and it has the same structure as another very important algorithm we'll study shortly called Dijkstra's algorithm. And so it's very important to understand the bookkeeping. How does the bookkeeping find the minimum weight edge? How does adding this new node to the tree update the bookkeeping? And so how is the bookkeeping maintained? What are the invariants? How are they maintained? Why is the heap necessary? How does the complexity come about? These are all important facts that you need to understand. I have presented it in a very high level manner. Now it's time to go into the book and study this algorithm a little bit more in detail. Hopefully it makes sense. Hopefully the bookkeeping makes sense. Hopefully the steps of the algorithm make sense and the complexity analysis makes sense. This is super important. I urge you to go look at the book, refer to this video lecture, and hopefully it can be clear. Taking an example and working through it will also help. So see you in the next lecture, where we will briefly look at the other algorithm called Kruskal's algorithm. Okay, see you then. Bye.